This video introduces two of the basic rules for proofs in QL: universal elimination and existential introduction. In the previous video, we discussed how the proof system for QL builds on the proof system for SL, and it's going to add 4 new basic rules for the quantifiers and 1 new replacement rule. This video covers 2 of the new rules. It's going to cover the elimination rule for the universal quantifier and the introduction rule for the existential quantifier, because those are 2 of the easier rules that we're going to have to add. Let's start with universal elimination. Suppose you have for all x fx on line 1. What can you conclude? That is, if you were going to eliminate that universal quantifier, what should you be allowed to write down? It may be tempting to say you can conclude that everything in the universe of discourse is an f. Remember, though, that a universe of discourse is something we only have in the semantics, that is, within models. In a proof, you can only write down sentences of QL. So, which sentences of QL should you be allowed to write down if you already have or know for all x fx? If everything's an f, it follows that C is an f. So you can write down FC. FD follows too. And so does FE. Because if for all x fx is true, then it follows that for any constant, f followed by that constant is also true. So if we've proven for all x fx, it follows as a consequent f followed by any constant. The universal elimination rule lets you rewrite the sentence without the quantifier, where you replace the variable with a constant. And you get to pick the constant. So which constant should you use? It depends on what you're trying to show in a particular proof. This is what the rule looks like on the reference sheet. If you have a universally quantified sentence, you can remove the quantifier, you can eliminate it from the front of the sentence, write down the rest of the sentence, replacing that variable with a constant of your choice. Consider this example. Given SA arrow not TB and not TA, and for all x SX or TX, we need to prove SB. So we start the proof in the usual way. We write down the 3 given sentences, and we need to end with the conclusion or the goal sentence, which is SB. So the question is, what can we do with these 3 sentences we have already, with the 3 premises? What rules could we apply to the first 3 lines to get something else that might be useful? Now, you might want to pause the video at this point, take out the reference sheet, and try to figure it out for yourself. What moves could we make from here? I'm assuming you've already resumed the video or decided not to pause. Looking at lines 1 and 2, there's nothing we can do with them immediately. The arrow elimination rule requires both the conditional and the antecedent of the conditional, but we just have the conditional itself. Negation elimination requires a subproof, and we can't use it on line 2. So line 3 is a universally quantified sentence, and universal elimination doesn't require anything more than that. So we'd be entitled to write down any instance. We could pick any constant, plug it in for x, and eliminate the universal. If we choose the constant a, then we can write down SA or TA. The justification, the rule we write down, is universal elimination applied to line 3. Does that open up any new possibilities for us? Well, what would it take to eliminate the disjunction on line 4? Well, disjunction elimination says you have to have a disjunction, an or sentence, and you have to have the negation of one of the disjuncts. And we have that. On line 4, we have the disjunction, and on line 2, we have not TA. So that lets us write down SA. The rule that justifies that is or elimination, 4, 2. So now we do have the left-hand side of that conditional from line 1. So that lets us write down not TB by arrow elimination, line 1 where we have the conditional, and line 5 where we have the left-hand side, the antecedent. So now what? Something to remember is that even though we've used universal elimination on line 3, we could do so again. We used it with the constant a before. We could also use it with the constant b. So if we use it for b this time, we get to write down SB or TB. Again, the justification is universal elimination, and it's applied to line 3. Now, looking at line 7, it's a disjunction. In order to use disjunction elimination, we need the negation of one of the disjuncts. But we have that on line 6. So disjunction elimination applied to line 7 and line 6 gives us SB. And that's what we wanted, so the proof's done. Now, this proof could easily have looked a little bit different if someone else had done it. For example, the universal elimination on line 7 could have happened much earlier. We could have made line 4 be SB or TB. And if we'd done that, we still would have had to get around to doing the same things. It would have changed the order of the steps, and it would have changed the line numbers that were referenced when we applied rules. I'm sure there are other ways to do the proof also, though. There are probably ways that would look very different using some of the derived rules or replacement rules. But there's no bonus for coming up with extraordinary or exotic proofs. In the end, all we need to do is show that there's a way to get from the premises to the conclusion, from the given sentences to the one we need to prove, following the rules. This proof does that, and that's enough. Okay, now let's consider existential introduction. What would you need to know? What would you have to have happen in the proof before you'd be allowed to write down exists x fx? Well, you'd need to know that something was an f, because if something were an f, you'd know that exists x fx was true. For example, if you had fa, then you should be allowed to write down exists x fx. So that's our existential introduction rule. Given some sentence that has a constant in it, you're allowed to write down a sentence that starts with an existential quantifier and then replaces the constant with a variable. Here's what it looks like on the reference sheet. We start with some sentence A that has a constant C in it. We then write down exists x, A, where we've got x in place of C. It says at the bottom, note that x may replace some or all occurrences of C in the sentence A, C. That is, the variable can replace the constant everywhere in the sentence or just in some places. So consider this example. Suppose we start with RAB arrow FA. We can apply existential introduction, replacing both of the A's. We could say exists x, RXB arrow FX. Or if we wanted, we could just replace the first A. We could say existential introduction on 1, exists x, RXB arrow FA. Or we could just replace the second A, exists x, RAB arrow FX. Alternately, we could replace B to get exists x, RAX arrow FA. All of those are legal applications of existential introduction. Which of these are things we'd want to do, which ones would help us, depends on what we're trying to prove. Here I'm just trying to show you how the existential introduction rule works. What we can't do, what you aren't allowed to do with the existential introduction rule, is replace two different constants with the variable. You get to pick one constant. You can either replace it everywhere it appears, or you can replace it just some of the places. You don't get to replace two constants with one application of existential introduction. If you want to apply it to different constants, you can apply the rule multiple times. So here, I've started with RAB arrow FA. I applied existential introduction to replace the a with a variable to get exists x, rxb, arrow fx. And then if I want to replace the b with a variable, I do it again. I apply existential introduction to line 2 to get exists y, exists x, rxy, arrow fx. And again, whether I'd want to do that depends on what kind of thing I'm trying to show in the particular proof I'm working on. So let's consider a specific example. Given for all x, rxa, and exists x, rxx, arrow exists x, fx, we want to prove exists x, fx. We begin the proof in the usual way. Well, there are a number of approaches we might take. One approach is to think about the goal sentence, exists x, fx. How will we eventually be able to write that down? One idea is that maybe we'll use existential introduction. We introduce the existential quantifier, exists x, fx. What would we have to have just before that? Well, given the way the existential introduction rule works, we'd have to have some instance of fx. For example, we could have fa. But where could we get fa from? It's not actually clear. So instead of working backwards, let's start at the top and see what we can get. Line 1 is a universally quantified sentence. If we eliminate the universal, we use universal elimination on line 1, it lets us replace that x with any constant we want. Let's try a. So we write down RAA on line 3. Notice we can get exists x, rxx from RAA by existential introduction. That's the antecedent of the conditional that we have on line 2, so we can apply the arrow elimination rule. It lets us write down exists x, fx, arrow e, applied to line 2, comma, line 4. We're done. Now, if you're working the proof out yourself, I wouldn't necessarily expect you to get it this quickly. Typically, there's some trial and error involved. When you understand what the rules allow you to write down, you can try things out. And it will often take several tries before you hit on a way that works. This video covered 2 of the new rules. And soon we'll have a complete proof system for QL.